In this video, we'll go over numerical differentiation. After studying this video, you should be able to derive finite difference formulas from the Taylor series. And these are approximations of derivatives. And you should be able to predict the behavior of the truncation error for various finite difference differentiation formulas. And we'll define that term truncation error in a couple minutes. First, let's talk about some applications of numerical differentiation. So one application is to differentiate discrete data directly. For example, tabulated properties like thermodynamic properties or experimental data. Can also use numerical differentiation techniques to compute derivatives of functions that are difficult or impossible to differentiate analytically. Probably most important is to understand numerical differentiation as a basis for other numerical methods. We've looked at two cases so far where we've used finite difference formulas, both in the secant method for roots problems and in developing a finite difference Jacobian matrix for Newton-Raphson. A wider array of finite difference approximations are going to be used in developing algorithms we'll look at for numerical methods for differential equations, and that topic is coming soon in this class. So let's start by reviewing the definition of differentiation. The mathematical definition of a derivative begins with a difference approximation. So if we look at delta y, the change in y, over the change in x of a function, we can evaluate that as f evaluated at x plus delta x minus f of x, all divided by delta x. And as we allow delta x to approach 0 and take the limit, that difference becomes a derivative. And this is the definition in calculus. And as we do that, that slope that starts out as being a secant line on the curve eventually goes to a tangent line that is the slope of the curve at that point x. So you learned in calculus how to take derivatives using various analytical techniques. And what we want to look at now is how we can take some numerical techniques to calculate a derivative. So the simplest approach would be just to drop the limit and use a finite delta x. Instead of taking the limit as it goes to 0, we will just drop the limit, use a small delta x close to 0, and recognize that we're going to have some sort of error. And what we want to do is know, well, what kind of error is this approach going to give us? So how much error? And can we improve on this approach? So in order to get an understanding of the error, the place we'll look is the Taylor series. So recall from calculus, we can use the Taylor series to predict the next value of a function. So the function evaluated at some xi plus 1 is going to be f of xi plus f prime of xi, so that's the derivative at xi, times h, where h is our delta x, the difference between xi plus 1 and xi, plus the second derivative of f over 2 factorial times h squared, and so on. And so you can look, this graphic kind of illustrates how the Taylor series works. If we take a zero-order Taylor series, it's just saying that f of xi plus 1 is equal to f of x of I. A first order would just use the first derivative term here, and we'd be approximating the function as a linear function from xi to xi plus 1. The second order Taylor series brings in some curvature with the second derivative, and if we used all of the terms from the Taylor series, we'd have the exact value of the function at xi plus 1. So we can use the Taylor series to understand, going backwards, what type of error we're going to have when we take this derivative. So here's the Taylor series again, and we can use it to derive that finite difference approximation that we get by just taking a finite delta x. And the way to do that is we would just solve for f prime. So if we solve for f prime of x, we get f prime at xi is equal to f at xi plus 1 minus f at xi, all divided by h, which again, that h is just our delta x. And then, so we've brought all that over, and then we're going to have these terms left over, which I will write as plus f double prime xi over 2 factorial times h, because we've divided out one of those h's, plus, and this is terms of order h cubed and higher. So that's like these terms, just going on out to the infinite number of terms in the Taylor series. So we'll just take the leading term and keep track of that. So what we see here is our finite difference approximation. That looks just like f of x plus delta x, and we have a measure of the error over here. So this is now order h squared, and so we can see that overall the error is proportional to h, or proportional to delta x. And one way to look at this is we've developed this finite difference approximation by truncating these terms of the Taylor series. So we've essentially truncated or cut off those terms starting with the h squared term of the Taylor series, and when we do that and divide through by the h, we see we have an error proportional to h, and we'll call that the truncation error. And we'll go ahead and call this term then a first order, because it's proportional to h to the 1. So it's a first order, and we're looking forward to xi plus 1 to calculate the finite difference. So it's a first order forward finite difference approximation. So that's we're just going to lump all those higher order terms into some order h, so we know it's first order. So we can kind of go forward from this approach and use the Taylor series to come up with other finite difference approximations. In this example, we used it to get an understanding of the truncation error that we got when we simply introduced the finite difference approximation in the first place. But we can also use the Taylor series to develop additional finite difference approximations and to understand how they behave. So let's look at a couple. So here's our forward finite difference, again first order. So to look at how what that's really doing is if we're trying to find this derivative at x sub I here, so here's f of x sub I, we're using the result at f x I plus 1 to estimate that derivative. So we are approximating the derivative. This would be h, the difference between xi and xi plus 1, and we're approximating that derivative with the secant line on the curve there. We know the true derivative looks like it's pretty darn close to 0 on this function, so that would be the true slope df dx. So our our approximation would have some error there, and again, that error is proportional to h. We can develop a backward difference formula just by going backwards with the Taylor series and get a difference formula that looks at f of x I minus 1. And so that would look over here, we take f of x I minus 1 and approximate that derivative with that error. Sorry, with that secant line. So we see both of these are obviously going to have some error, and the error is going to get smaller, decreases proportional to h. So if the error is 0.5 and we reduce h, so let's say ET, or true error, is equal to 0.5 at h equals 0.1, and then we take h equals 0.05, so we cut h in half. That means that we could expect our true relative error to be equal to 0.25. Sorry, that's our true error, not true relative error. So one thing you might notice looking at this picture is, well, what about, it looks like if we took f of x I minus 1 and f of x I plus 1 and bracketed xi, that would be what we would call a center difference. If we center our 2 points across the point that we're approximating, looks like we get closer to the result. And in fact we do. And again, we could look at the Taylor series to look at how that works. So here's a center difference where we will bracket the points. We'll bracket xi. So we're taking the derivative at xi, but we're using xi plus 1 and xi minus 1. So let's get an understanding of what the truncation error is going to be for this case. So now we are, again, taking that point fxi minus 1 and fxi plus 1 and using that approximation to approximate the slope here f prime at xi. And just looking at the picture, since they're on either side, and for this particular case, and it's generally true, it looks like it'll be more accurate. And we can look at the Taylor series expansion for both of those cases. So here's the Taylor series expansion for f of x I plus 1 and the Taylor series expansion for f of x I minus 1. And if we call this equation 1 and this equation 2, and what we'll do is subtract equation 2 from equation 1 and solve for f prime at xi, and what we get is f prime at xi is equal to, so if you imagine doing this, the f of xi's, these are going to cancel when we subtract these two, and when we subtract here, we're going to get that 2h that shows up on the bottom, and we're going to get f at xi plus 1 minus f at xi minus 1, all divided by 2h. And then let's look at what happens to the truncation error terms. For the h squared term, we're going to square that negative h. So again, these terms are going to cancel out, because when we square that negative h, these terms are going to be identical, and they're going to cancel out, and we're left with the h cubed terms. And then when we divide through by h, we're going to have just an h squared term. So this will be order h squared. So we see that the centered finite difference formula is going to be order h squared, or second order. So what that's going to mean is, in that same case, if we started with an h equal to, so if we started with an error of 0.5 with h equal 0.1, so if we started with an error of 0.5 with h equals 0.1, and then we reduce h to 0.05, basically cutting h in half, then since this is h over 2, our ET, our new error, is going to be equal to the old error, ET, or 0.5, divided by 2 squared. So that's where our second order behavior is, so that ET, our new error, once we cut h in half, would be approximately 0.5 over 4, or 0.125. So that's an indication of what happens when we go to a second order finite difference approximation. And we can look at going to higher order approximations, and there's really a whole series of Taylor series gymnastics we can do. We'll just go through one more example. Oftentimes we need to have a forward difference or a backward difference approximation. So if we wanted to come up with a second order forward difference approximation, so using f at xi, f at xi plus 1, and f at xi plus 2, to come up with a derivative approximation at f of xi. So we're going to try and again approximate that derivative at f prime at xi. And what we can do is we'll start with these two equations. So what I have here we'll call equation 1 is just the Taylor series expansion for xi plus 1, and equation 2 is the Taylor series expansion for xi plus 2. And what I'm going to do is start by eliminating the f prime term. This might seem counterintuitive, but you'll see where we're going here in a minute. If we eliminate the f prime term by taking equation 2 minus twice times equation 1, so we get f at xi plus 2 minus 2 f at xi plus 1 is equal to, and here we have f of xi minus 2f of xi, so this becomes minus f at xi, and f prime xi times 2h minus 2 times f prime xi times h, so that's going to cancel, and then we have f double prime of xi times 2h squared minus f double prime xi times h squared, but this is times 2, this is 2 is going to become a 4, and so what we're going to have left there is a 4 over 2 factorial minus a 2 over 2 factorial, or 2 minus 1, and we're just going to have plus f double prime of xi times h squared plus terms order h cubed and higher. And what I'm going to do with this term is solve now for f double prime, and we'll plug that back in to our first term and solve for f prime. So if we solve that for f double prime, we get the second derivative of xi is equal to f of xi plus 1, f of xi plus 2 minus 2 f of xi plus 1 plus f of xi, all divided by h squared plus terms order h, because now we've divided through by h squared, so that drops the h cubed down to an h. So I'll call that equation 3, and I'm going to substitute 3 for f double prime in equation 1, and what we get when we solve for f prime at xi is f prime at xi is equal to negative f xi plus 2 plus 4 f at xi plus 1 minus 3 f at xi, all divided by 2h, and then we're going to plug that order h back times the h squared right here, so what we've got left, and then divide through by the 2h here, so we're actually going to end up with a truncation error order h squared. So this then gives us a second order finite difference approximation that's a forward difference, looking forward 2 points from x to approximate that derivative at f prime. So this gives you an idea of how you can just kind of play some algebraic gymnastics with the Taylor series to come up with various finite difference approximations. It's important that you understand how to do this, but there's no real need to reinvent the wheel. This has all been done before. And so what I've got here are some tables of various finite difference formulas. One thing I might note is, notice along the way here we developed a finite difference of first order. That's going to be a first order forward difference approximation for f double prime at xi. So we came up with a finite difference approximation of the second derivative along the way. So here's some tables for your reference. These are forward finite difference formulas, and here's the truncation error over in the right column. So we have looked at that forward finite difference. We just derived the second order forward finite difference, and here's the first order finite difference of the second derivative that we also just derived, but we could come up with a second order finite difference for the second derivative and on for third derivative and fourth derivative if we wanted. These are the backward finite difference formulas. They kind of look like a mirror image, which is not too surprising, of the forward finite difference formulas. And again, here's that backward difference, which is first order, and you can see the second order backward difference looks pretty similar to what we just derived. And lastly, we have the centered finite difference formulas, and you'll note the centered finite difference formulas are in general a little bit higher truncation error. So again, that means they are more accurate, as we saw earlier. That's generally true. So in fact, one really common one to use is a fourth order centered finite difference formula, because this can give us pretty accurate results for relatively large values of h, like h around 0.1 or something like that. So you can use these tables for reference to apply these high order finite difference formulas for calculating derivatives. And we'll talk more about the error behavior of how these approximations work in the next video.